Welcome to the deep dive. Last time, we really got into time complexity, how we measure an algorithm's speed.
Right.
Today, we're looking at the flip side, space complexity. It's like an algorithm doesn't just need time. It also needs memory, elbow room in your computer's memory to actually work.
Exactly. It needs space to operate.
And this deep dive is all about really understanding how algorithms use that memory. We want to equip you with knowledge that hopefully really sticks for the long term.
That's the goal. While time complexity tells us how runtime scales, space complexity is about the memory footprint, how much RAM it's going to need as the input grows.
Okay.
So our mission today really is to dissect this. We'll look at calculating it, the common patterns you see, and that crucial dance between space and time. The resources we've pulled together give a pretty detailed view. So yeah, by the end, you should have a solid, lasting grasp.
Fantastic. So before we dive too deep, maybe paint a quick picture. Where does an algorithm actually use memory?
Good starting point. Generally, you've got three main areas. There's the input space for the data you initially give it.
Right, the starting stuff.
Then there's temporary space, which is like its scratch pad while it's working. And finally, output space for the result.
Okay.
Now, when we talk space complexity analysis, we usually focus most on that temporary workspace and the output space. The input space is often considered separately.
Got it. So let's unpack that temporary space then. What are the ingredients there? What's it made of?
Right, so think of temporary space as the algorithm's workshop. It's got a few key parts. First, temporary data.
Okay.
This is all the short-term stuff. Constants, variables that change values, objects it creates just for processing. Like if you see code like A or B equals 0 or node equals 0, the memory holding A, B, and that node object, that's temporary data.
Okay, so like the little notes and values it needs while it's doing its calculations. Makes sense. What else is in that temporary workshop?
The next really crucial bit is stack frame space.
Yeah.
This pops up every single time a function gets called.
Every time.
Every time. Imagine like a stack of plates. Calling a function adds a new plate, a stack frame to the top. This frame holds everything for that specific call. It's local variables, parameters passed in, where to go back to when it's done. And what's interesting is each new call creates a new frame piling up. This memory only gets freed when the function finishes and returns, and its frame is popped off the stack. So if your code has, say, C function, the space for that function's stack frame, that's part of our temporary space budget.
Right. So each function call gets its own little temporary memory bubble. That clarifies things. Was there a third talk you mentioned?
Yes. The last piece is instruction space.
Yeah.
This is memory for the compiled program instructions themselves, the actual code the computer runs.
The recipe base.
Exactly, the recipe. But usually when we're analyzing how memory scales with input size, this instruction space is kind of a fixed cost. It doesn't really grow if you give the algorithm more data.
Okay.
So for complexity analysis, we really zoom in on temporary data, stack frame space, and of course the output space needed.
Okay, that gives us a really clear picture of where the memory goes. Now, how do we actually calculate this space complexity? Is it similar to how we figured out time complexity?
It shares some core ideas, yeah. The main goal is the same. Find out what factors most impact how memory usage grows with the input size, usually denoted by n.
Right.
But instead of counting operations, like we did for time, we're measuring the size of the memory being used. How much space does it take up?
Makes sense. Tracking memory scale instead of time scale. Now, the sources really stress that we typically focus on the worst-case space complexity. Why is that the main focus? Why the worst case?
That's a really critical point. Unlike time, where maybe an average performance is okay sometimes,
Yeah, sometimes average is fine.
running out of memory is usually catastrophic. It just stops. Game over.
Yeah.
So we need to be pretty confident the algorithm can run, even with the input that makes it use the most memory. We analyze the maximum potential memory need.
To guarantee it won't just crash.
Exactly. Now, worst case here actually has sort of two angles we need to consider for a full understanding.
Okay. Two angles. Tell me more.
So first, worst case can mean the specific type of input data that forces the algorithm to use the most memory possible. Imagine an algorithm creating an array, let's call it nums.
Okay.
Maybe its size depends on an input n. If n is small, maybe less than 10, the array is fixed size, uses O1 space constant space. But if n is large, say over 10, maybe the array size is n. That's O(n) space, linear space.
I see.
In that case, the worst-case space complexity, considering all possible inputs, is ON, because that's the biggest memory demand we might face depending on N. It's about finding the input that makes it the most memory hungry.
Right, so the input that really pushes its memory limits. What's the second angle on worst case?
The second meaning looks at the peak memory usage at any point during the algorithm's run, even if it cleans up later.
Okay, the highest point it reaches.
Precisely. Let's use that nums array again. Maybe it creates this big ON array early on, but then later it processes it and doesn't need it anymore, freeing the memory.
Right.
Even though it might end up using very little memory at the end, the fact that it needed ON space at one point means the worst-case space complexity is still ON. It's about the high watermark.
That's a great way to put it, the high water mark.
Yeah.
Not just the final state.
Okay.
Okay. Now, the sources also specifically call out recursive functions. We need to pay extra attention to them and their stack frame usage. Why is recursion special here?
Absolutely. Recursion adds a unique twist because of how it uses that call stack we talked about.
Clates piling up.
Exactly.
Yeah.
Every time a recursive function calls itself, a new stack frame gets added. If it makes many, many nested calls before any of them finish and return, well, those frames pile up significantly.
Like Russian dolls getting deeper and deeper.
Precisely. Think about two hypothetical functions, loop and recur. Let's say both do something n times, so their time complexity is the same, O n.
Okay, same speed.
But their space complexity can be totally different.
How so? Loop uses iteration,
Yeah.
uses recursion.
Right. The loop function, using iteration, might call some other function inside its loop n times, but often that called function returns each time its stack frame is removed, maybe reused. So at any single moment, you probably only have one active frame for that called function, plus whatever the loop itself uses. Often, that results in O1, space, constant space.
Okay, it cleans up after itself each time.
Kind of, yeah. But recur, calling itself n times, usually doesn't return until it hits a base case, the stopping condition. This means you could have n active calls to recur, all sitting on the stack simultaneously, waiting.
All waiting to finish.
Exactly, each with its own stack frame, its own local variables, so the total space taken by these piled up frames grows with n. That gives us ON, space complexity, linear space, just from the stack frames.
Wow. Okay, so same time complexity, potentially very different memory footprint. That's a really clear and important distinction. Recursion can be elegant, but memory hungry sometimes?
It definitely can be. It's a hidden cost you need to be aware of.
Right. So let's shift gears a bit. Let's talk about the common types of space complexity we see. Like with time, there are these categories describing how memory scales, right?
Yes, exactly. We see similar patterns. The common orders, generally going from least memory usage growth to most, are O1, O log n, ON, ON, and O2.
Okay, let's walk through those. Starting with O1, constant order. What does that look like?
O1, constant space, means the algorithm uses the same amount of memory regardless of the input size n. It's fixed.
Like needing the same toolbox for a small job or a big job.
Perfect analogy. The number of tools doesn't change. This happens when you use a fixed number of variables, constants, maybe data structures that have a set size. Like that constant function example we touched on, it might declare a constant A, a variable B, maybe even a large array nums, but a fixed size, say 10,000 elements. That's still constant size, and maybe an object node. The memory for each is fixed. And crucially, even if you have loops that declare variables inside them or call functions inside, if those variables get reset each iteration, or the function calls finish and release their stack frames each time, the total memory used doesn't accumulate, it stays O1.
Okay, that's key. Reusing memory or letting it go keeps it constant overall. Got it. What's the next step up in memory usage?
Next is linear order, ON. Here, the memory usage grows directly in proportion to the input size n.
So double the input, roughly double the memory needed.
Pretty much, yeah. Think of leading a bigger shopping cart if you want to buy more items. This is super common when you store the input data or intermediate results in structures like arrays, linked lists, stacks, queues, where the number of elements depends directly on n. That linear function example, creating an array nums of size n, or a hash map that might end up storing n things, both need ON space. And remember, linear recur.
The recursive one.
Yeah. It's n nested calls piled up n stack frames, also leading to ON space. So memory grows in a straight line with input size.
Okay, so holding collections of data tied to the input size often means ON. What if things need to grow even faster?
Then we might hit quadratic order, ON tor. This often happens when you're dealing with things in two dimensions, where both dimensions relate to n.
Like a grid or a matrix.
Exactly. Matrices are a classic example, or certain ways of representing connections in graphs. Our quadratic function example showed creating a 2D list, like an n by n matrix, in a matrix. That clearly needs n times n, or on, space.
Okay.
And recursion can get you there, too. The quadratic recur example involved n levels of calls, and each call created an array roughly proportional to n, or n1, n2. Adding all that up leads to on space overall.
Right, so nested structures or recursive calls where both the depth and the work done at each step scale with n can land you in ON territory.
Okay, and I know things can get even more explosive.
Explosive is a good word for it. Next is exponential order, O2. This is where memory needs can really skyrocket. You often see this in algorithms exploring all possible combinations or subsets of the input, or with certain tree structures, like a family tree branching out wildly.
Kind of, yeah. Think about building a full binary tree. Our build tree example illustrated this. If a full binary tree has n levels, it has roughly 2 nodes.
Wow.
Since each node takes up space, storing the whole tree requires O2 space. This kind of growth is incredibly rapid. Algorithms with exponential space complexity become impractical very, very quickly, even for moderately sized inputs. They hit memory limits fast.
Definitely a red flag for memory. Okay, we skipped one O log n, logarithmic. We saw that's often efficient for time. How does it look for space?
Logarithmic space, O log n, is often quite efficient for memory, too.
Yeah.
You frequently see it with divide and conquer algorithms. Remember, merge sort, its time is O(n) log n, but the space needed just for the recursion stack frames is only O log n.
Why log n?
Because the depth of the recursive calls, how many levels deep it goes before hitting the base case, is logarithmic relative to the input size n. It keeps having the problem.
Ah, okay. The number of stack plates doesn't grow as fast?
Exactly. Another place you see O log n space is sometimes just converting a number, n, to a string. The number of digits in n is roughly proportional to log base 10 of n. Each digit takes constant space, so the whole string takes O log n space.
Interesting. So algorithms that cleverly divide the problem can be memory efficient too.
Mm.
Okay, we've covered the main categories. The sources also really highlighted this interplay between time and space. The space-time trade-off, this sounds pretty fundamental.
Oh, it absolutely is. It's one of the core challenges in algorithm design. Ideally, we want algorithms that are lightning fast and use hardly any memory.
The dream scenario.
Right. But in reality, there's often a trade-off. Making something faster frequently means using more memory, and trying to squeeze memory usage might mean it takes longer to run. That's the space-time trade-off. It's a balancing act.
A give and take. Can you give a concrete example?
Sure. A classic one is using hash maps or hash tables for fast lookups. If you need to search for things in a big data set really often, a hash map can give you almost O1, constant time, searches on average, super fast.
Yeah, hash maps are great for speed.
But they need extra memory. You need space for the hash table itself, maybe to handle collisions, so you're sacrificing space for that speed. That's a space-time trade-off.
Okay, using more space to save time.
Exactly. The alternative might be just searching through a simple list. That uses very little extra memory, maybe O1, but finding something could take ON time, in the worst case, much slower.
Right.
The opposite, a time-space trade-off, might be deciding not to store some calculated value, saving memory, but then having to recalculate it every time you need it, which takes more time.
Got it. So how do you decide, is faster usually better, even if it uses more memory?
It really, really depends on the context. What are the constraints? What's the goal? In a lot of modern applications with plentiful RAM, time is often seen as more critical. Users want speed.
So the space-time trade-off, more memory for speed, is maybe more common?
Often, yes. Think web servers. Big data processing where throughput matters. But, and this is a big but, you can't ignore space complexity, especially with truly massive data sets where even ON space might be too much. Or think about embedded systems like in your car or a medical device or mobile apps. Memory is often very limited there.
Right, resource-constrained environments.
Exactly. In those cases, minimizing space might be the absolute top priority, even if it means the algorithm runs a bit slower. You have to fit within the memory budget.
That's a really crucial point. Memory might seem cheap, but it's not infinite, and sometimes it's very restricted.
Yeah.
Okay. Well, this has been incredibly thorough, a real deep dive into space complexity, hopefully giving everyone that lasting understanding we aim for. To wrap things up, could you just quickly recap the absolute key takeaway?
Sure. We defined space complexity,
Yeah.
how memory needs scale with input size. We broke down where memory is used, focusing on temporary space, data and stack frames, and
Mhm.
output space. We talked about worst case analysis, both for tricky inputs and peak usage during runtime. We highlighted recursion's impact via the call stack. Then we walked through the common orders, O1, O log n, O n, O no 2 gid with examples. And finally, we discussed that fundamental space-time trade-off, the balancing act between speed and memory usage.
Perfect. And just like understanding time complexity helps you write faster code, understanding space complexity lets you make really informed choices about memory, leading to more robust, more scalable software. So, for our final thought today, maybe mull this over. Can you think of specific scenarios beyond the ones we mentioned where minimizing space is absolutely non-negotiable even if it costs you speed? Consider systems where failure isn't an option or where data is so vast it fundamentally changes how you approach storage. How would those constraints force you to design algorithms differently than if you were just optimizing for raw speed? Something to ponder. Thanks for joining us for this deep dive.